Lesson: Architecture of Artificial Neural Networks. The architecture of artificial neural networks is integral to the field of artificial intelligence, providing the backbone for numerous applications in deep learning. At their core, ANNs are computational models inspired by the human brain, composed of interconnected nodes or neurons, which process information in a manner akin to biological systems. Understanding the architecture of these networks is crucial for professionals seeking to harness the power of AI to tackle real-world challenges effectively. The fundamental unit of an ANN is the neuron, which receives input, processes it, and produces an output. Neurons are organized into layers: the input layer, one or more hidden layers, and the output layer. Each layer's neurons are connected to those in adjacent layers, enabling the network to learn complex patterns from data. The architecture of a neural network can be adjusted by varying the number of layers and neurons, which in turn affects the network's capacity to learn and generalize from data. A critical aspect of neural network architecture is the activation function, which introduces nonlinearity into the model, allowing it to solve complex problems. Common activation functions include the sigmoid function, hyperbolic tangent, and the rectified linear unit. The choice of activation function can significantly impact network performance. For instance, ReLU is often preferred in deep networks because it mitigates the vanishing gradient problem, a challenge where gradients become too small for effective learning. Training a neural network involves adjusting the weights of the connections between neurons to minimize the error in predictions. This process is typically carried out using backpropagation, an algorithm that calculates the gradient of the loss function and updates the weights accordingly. Optimizers such as stochastic gradient descent, ATOM, and RMSProp are employed to improve the efficiency of this process. ATOM Optimizer, for example, is widely used for its adaptive learning rate, making it suitable for handling sparse gradients and noisy data. The architecture of a neural network also includes the consideration of regularization techniques to prevent overfitting. Overfitting occurs when a model learns the training data too well, including its noise, and performs poorly on unseen data. Techniques such as dropout, which randomly sets a fraction of neurons to 0 during training, and L2 regularization, which adds a penalty to the loss function for large weights, are commonly employed to address this issue. Convolutional neural networks represent a specialized architecture designed for processing grid-like data such as images. CNNs utilize convolutional layers, which apply a set of filters to the input to detect patterns such as edges or textures. These networks are particularly effective for image classification tasks, as demonstrated by their performance in benchmark datasets like ImageNet. CNNs have been employed in various real-world applications, including medical image analysis and autonomous vehicles, due to their ability to capture spatial hierarchies in data. Recurrent neural networks are another specialized architecture designed for sequential data processing, such as time series or natural language. RNNs possess loops in their connections, allowing information to persist, making them suitable for tasks where context is crucial. Variants like long short-term memory networks and gated recurrent units have been developed to address the vanishing gradient problem in standard RNNs, enabling them to learn long-range dependencies effectively. Frameworks such as TensorFlow and PyTorch have become indispensable tools for building and training neural networks. TensorFlow, developed by Google, provides a robust platform for deploying machine learning models across various environments, from cloud servers to mobile devices. Its high-level API, Keras, simplifies the creation of complex models, making it accessible to both beginners and experts. PyTorch, on the other hand, is known for its dynamic computation graph, which offers flexibility and ease of use, particularly for research and experimentation. In practice, selecting the appropriate neural network architecture involves understanding the problem domain, data characteristics, and computational resources. For instance, a simple feed-forward network might suffice for a basic classification task, while a more complex architecture, like a CNN or RNN, might be necessary for image or sequence data. Tools such as AutoML can assist in automating the model selection and hyperparameter tuning process, allowing practitioners to focus on data preparation and interpretation. Case studies highlight the impact of neural network architectures in real-world scenarios. In healthcare, CNNs have been used to develop models that can diagnose diseases from medical images with accuracy comparable to human experts. For example, a study by Esteva et al. Demonstrated the application of a CNN in identifying skin cancer, achieving performance on par with dermatologists. Similarly, in finance, RNNs have been employed to predict stock prices by analyzing historical data and identifying patterns indicative of future trends. The architecture of neural networks continues to evolve, driven by advancements in AI research and increasing computational power. Techniques such as transfer learning, where pre-trained models are fine-tuned on specific tasks, and the development of novel architectures like transformers, which excel in natural language processing tasks, are shaping the future of neural networks. As these architectures become more sophisticated, they hold the potential to revolutionize industries by providing solutions to complex problems that were previously insurmountable. To conclude, the architecture of artificial neural networks is a dynamic and multifaceted area that requires a solid understanding of the underlying principles and practical tools available. By mastering these concepts, professionals can leverage the power of neural networks to address real-world challenges, innovate within their fields, and contribute to the advancement of AI technology. Whether through the application of CNNs in image recognition, RNNs in sequence prediction, or the use of frameworks like TensorFlow and PyTorch, the possibilities are vast and continually expanding. As the field progresses, staying informed about emerging architectures and methodologies will be essential for those seeking to maintain a competitive edge in the ever-evolving landscape of artificial intelligence.